Awesome. So last week, my name's Will Fisher. George and I will be attending all these classes. Normally I would. Last week, I wasn't able to attend. So just a little background on myself. I've been with FI for 10 years, going on 11 soon. I started off on our inside sales, outside sales, tech support, moved over to the engineering side about 6 years ago. Some folks may recognize my face. I go to a lot of AEE, ASHRAE events. I'm president-elect for Boston. So you go to the golf outings, you go to the monthly meetings. I'm sure we'll run into each other. And then the last session that we have, where we're going to look into heat transfer from heat exchangers to heat pumps to cogen, trigen. That's kind of where I'm going to try to do what I can to blend in a lot of what we're kind of leading into. So if anyone has any questions, during the break, feel free to pull George and myself aside, ask any of the questions you might have. Also, for anyone that's here, that's online, if you enter the chat, I'm going to try to man the chat. So if you see me typing away, I'm probably trying to respond to someone up there. But big thing is 3 hours to keep everybody awake if we can just be interactive. So if you have questions, don't think you're slowing anything down. We got the material. We can breeze through things as quickly as people get it and spend more time on things that might need a little bit more. So yeah, hopefully we match everybody's pace. It's always tough to do. So thanks for joining us.
So we're going to get going. Again, introduced myself last week, but George Carey, and we got a X number of friends joining us remotely, watching through the share screen, watching the PowerPoint presentation, as well as all of you. Similar to what we did last week, we'll probably stop for a quick bite to eat right around 5:30 or so, and take a 10-15 minute break, and then we'll get back at it. And so for everybody that's remote, give or take, I'll announce it, but probably right around 5:30, we'll stop for about a 10 or 15 minute break, and then we'll rejoin together and continue on and finish up this second week. The first thing I just wanted to go over just real quickly is some of the stuff we talked about last week, and then we'll kind of transition into some pumping fundamentals and some applications, et cetera. And to Will's point, Q&A, right? And hopefully informative, but a little bit informal. Come right in. Welcome. So stop us in our tracks if you got a question, or something didn't make sense, or whatever the case may be. For everybody remote, don't hesitate using that chat room, and we'll keep an eye on it for this week. So we just want to review real quickly. We started talking last week, just some of the basics about just the pump curve and understanding a pump curve and what that entails. And as we move into some of the subjects this week, it'll kind of follow right along, or follow right into it. So the first thing, just developing a curve. Typically on that bottom horizontal axis, we're referencing, or the pump curve is referencing flow rate. At the end of the day, what we're trying to do is trying to move energy from a boiler plant or a chiller plant, or whatever the case may be, out to terminal units to provide comfort, heating, or cooling. And the way we're going to do that in a hydronic system is we're moving water. How much water? Typically, we're going to measure it in gallons per minute is our flow rate, pounds per hour. All of these things we'll talk a little bit about. We referenced it last week. And then as you're moving that water through, typically in a heating or cooling system, it would be referred to as that closed loop system. So it's not open like a booster package or a domestic hot water going to showers or whatever the case would be. It's a closed a piping network. And so to move that water through your heat exchangers, your boilers, your chillers, your piping, there's frictional resistance. Not unlike air moving in, say, ductwork. There's the static pressure, there's resistance. So a pump curve is trying to represent, hey, what is the capacity of this particular pump? What is its footprints? What can it do? And then we take that information and say, okay, here's our condition. This is what we're trying to design around, solve a problem, provide whatever. Can this pump do what I need it to do, type of thing. So that's the real fundamentals of it. You kind of break it down to, okay, flow rate in the hydronic system, and we touched on this a little bit. We'll take just a little more, spend a little more time right at the very beginning of second week. But, you know, what is the flow rate? How do we establish that? And typically in a hydronic system, when we're dealing with either water or water glycol, there's a certain temperature, there's a specific heat of that fluid that we're using. And then what's the load? How many gallons, or what's the BTUs, I should say, that we're trying to either reject or provide in that space? You know, so there's different calculations. And then as you establish those calculations, how do they relate to flow rate? And then once we have flow rate, what size pipe? Once we have pipe, what's the pressure drop? What's the frictional resistance? Once I know all of that, I kind of calculate and then come up with a set of conditions that now I'm going to go specify or select and then specify a circulator or a group of circulators. So just a very simple formula, but when we talked about where it came from, BTUs per hour, you know, how do we establish either that or we kind of work backwards, but 500, which we said was the weight of a typical gallon of water, 8.34, 8.33 pounds per gallon. And we're talking BTUs per hour and flow rate in gallons per minute. So we have 60 minutes in an hour. So we're going to take that weight of a gallon of water times 60 minutes, and that's where we get this factor of 500. And then the last part we want to do is we want to times it by that delta T, that change in temperature, the BTUs, either cooling, and it arrives at a certain temperature, and then it experiences a temperature rise or temperature gain. And conversely, in a heating system, it leaves the boiler plant at a certain temperature, goes through its terminal units, fan coils, baseboard, whatever, radiant heat, takes a temperature drop and drops off those BTUs, if you will, and it comes back cooler. We kind of plug in all of those, and we can start to establish BTUs divided by a certain factor will establish a flow rate. And we'll get into that a little bit more. On the flip side, or the second part of the equation, I guess I should say, here's a quick example, closed loop. We got what's establishing a pump head in a closed loop system. And in this case here, someone's already done it and they said, hey, I need about 18.5 feet of pressure differential head capacity to move a certain flow rate through my closed loop heating or cooling system. So they'll say, okay, I've got some piping friction losses, and then I'll have components on KPDs. All it stands for is known pressure drops. I got a boiler, I got a heat exchanger, I have some control valves, I have a fan coil. Yeah, all of these components will have some type of established, hey, if you pump this many GPM through it, it's going to offer this type of resistance. We want to know that because we're going to have to account for that resistance to make sure when we select the circulator, it can provide that proper pressure differential, that head capacity to overcome the frictional resistance it will experience. The other part, and I kind of mentioned it last week a little bit, was just get comfortable with this concept of the system curve and then how to construct it, system curve construction. And it's really just talking about the known relationship that will exist in a hydronic system, a closed loop system where if I have a known flow rate and you've sat down and either mathematically with a calculator through some software, which typically is what we're going to use on a day-to-day basis, but we've calculated that known head loss. So now I have flow rate and head loss. If I change any one of those conditions, if I change the flow, either increase it or decrease it, I know I can mathematically calculate what that corresponding new head loss or friction loss is going to be. And that's how I can establish or develop a system curve. And that system curve is very specific to that system, that set of conditions that we established. So just a quick example, we talked about 200 gallons a minute at 30 feet ahead. And if I start plugging in on this formula here, perhaps some different flow rates, I can calculate and figure out the corresponding new pressure drops. And when I do that, I can plot, and software-wise, they do that consistently as you're selecting pumps online. We'll show a pump curve, and then we'll show the intersection of that system curve. And that's the relationship of this known set of conditions. What were they? As long as that is true, 200 GPM at 30 feet ahead, we can calculate any other set of conditions and plot that system curve relative to the intersection of the pump curve, because the pump has to operate somewhere on that impeller, on that curve. And ideally, we want to have the two intersect, and they will intersect. Hopefully where they intersect is the design conditions we're chasing after, or trying to accomplish. So that's just a real kind of a quick review. We're going to jump in. We ran out of time last week, and we wanted to talk a little bit about, just briefly, but the system size of that little wheel that came with each catalog or engineering catalog. And so those that are remote right now, obviously you might not have a wheel in front of you, and that's okay, because the slides that we're going to get into we'll actually have screenshots of the slides of these various set of conditions. But that's what we want to kind of hit real quick at the beginning here. But pump performance, you got an impeller diameter, and all they're saying here is I've established or I have a pump that can perform somewhere along this curve. Hopefully that is going to be, the system curve is going to intersect somewhere on that pump, and ideally where we want to operate. Real quickly, just how to read a curve. We're looking at, in this case here, it's a commercial pump, a base mounted end suction pump, and the size of it such that a 2.5 BB can support a full wheel. We talked about the full wheel, the full diameter that casing or that volute can support. In this case here, it's about 9.5 inches. And the manufacturer has tested and established that, hey, I can reduce that diameter down to about 7.25 inches. I really don't want to go below that, because I really start to impact the efficiency because of recirculation that will take place of that water right in the volute itself, because the wheel has gotten so small relative to the size of the casing. So you'll look at, when I look at curves, I look at impeller diameters and the performance. Each one of these is almost like individual pumps, but it's just one pump. Good afternoon, David. How are you? That's okay. Traffic. But we have impeller diameters, and how would read that? That's a pump curve. 9 inch, that's a pump curve. 8.5, etc. Over here, we're looking at horsepower. We have a certain requirement of horsepower to do the work of what the flow and head is. So when you're looking at this multiple pump curve with this multiple capacities, we also might require multiple motors, horsepower. And how do they influence, or how do we select the right motor relative to where are we on the curve? What are we trying to accomplish? You get into the efficiency, the reference or the expression you'll hear is BEP, best efficiency point, that the manufacturer has calculated, and then typically a third party like Hydronic Institute will test the pumps to kind of prove, yeah, they manufactured it, they said it can do this, we tested it, and it does do this. So it is third party tested. But so somewhere, ideally you're picking a pump somewhere in that range, but it doesn't have to be exact. But just understand when you're looking at what these efficiencies, as you move further away, either to the right or to the left, maybe at some point you say, you know what, this may not be the right pump. Maybe I need to go smaller or bigger to meet the needs I'm looking for. One last thing, and we'll try to get to that this afternoon at the end, is this thing called net positive suction head, or NPSH. And so on the pump curves, in addition to impeller diameters and efficiencies and motor horsepowers, we'll have this NPSH R curve, and that R stands for required. So that's coming from the pump manufacturer. They've done their testing, and they've said, okay, to move a certain amount of gallons per minute in this particular model, I'm going to experience a pressure drop. And that pressure drop is as the water enters the eye of the impeller and then comes into the volute, it's going to experience some pressure drop. So I want to make sure that what I have available is equal to or greater than what the pump manufacturer says is required. Because if it isn't, then the pump starts to cavitate. And if you might not have had the chance yet in your careers to get out in the field and experience cavitating pumps in a mechanical room, but once you do, you won't forget it. It's pretty memorable. And sometimes some of the pipe fitters or the mechanical contractors, they'll describe it when they're experiencing out in the field for various reasons, is it sounds like the pump is beating itself up It sounds like it's pumping marbles is another expression, but it's really, it's kind of venturing out into an area where it does not want to belong, or there's some set of conditions that are causing some of that water to change its state into a vapor. So that's just the last part of this curve, is this NPSH. And like I said, at the end of the evening or the end of the class night, we might be able to touch a little bit on just what that factor is all about. And then when you go in to pick those pumps, you know, these are just some preferred and acceptable operating range. We talked about the best practice in terms of from BEP -15, so to the left or to the right, 5%. Good practices. So there's some industry standards. You know, you don't have to be dead on. Ideally, get close, but here's some acceptable ranges. And we talked about this last week. So what I like, so just real quickly, this is just kind of pulling together a lot of those little factors about establishing flow, pressure drop, pipe sizing, stuff like that. I just want to work through this. This calculator has been around. I think we touched base on it briefly maybe last week, but it's in the engineering world, and maybe I'm repeating myself, but in the engineering world, a lot of the engineers over the years have been familiar with this thing called a ductilator, and it has to do with the air side of the business. And when they got familiar with this and started using it, it became kind of they refer to it as their pipelator, similar to the ductilator, but having to do with pipe sizing. And just the information that's contained on the wheel, which is nothing like proprietary or subjective. It's just a bunch of calculations that exist in charts and books and online now and within software. And a gentleman from Bell and Gossett years ago kind of put it together as just a useful tool. Today with software and stuff, you know, maybe doesn't have quite the allure that it did years ago. But we'll just go through it real quick. And actually, I mean, talk about history. The first B&G system sizer was 1939. And that really had to do with how to size a circulator in residential application when you were taking gravity hot water, which really existed quite a bit out here in the Northeast, because that's where heating systems started. And then they were converting them to putting a circulator, a booster pump to circulate the heat. But anyways, it's this wheel, it's a circular slide wheel, comes in a packet or a pocket, if you will. And it was developed by an engineer who worked at Bell and Gossett for 42 years and spent a tremendous amount of time with ASHRAE all across the country. And the moniker would have been father of modern hydronic. And I think I might have touched base on it, but that catalog that you would have received or will receive, if you haven't yet, all of those they refer to as TEH, Training and Education Hydronics, TEH manuals. This guy, Carlson, wrote, or he had his fingerprints on at some point over the years. So he was very, very involved, very capable within the hydronic world. And so he invented a bunch of different things that we kind of take for granted or use on a regular basis. So real quickly, obviously the wheel we're talking about, we'll get into next week, the whole primary, secondary, or primary, secondary, tertiary pumping was originated with Gill. Triple duty valves, circuit setter, balancing hydronic systems. Gill developed or had his hands in the developing of that first circuit setter. But over the years, and I mean quite a few years now, I mean hundreds of thousands of these have been passed out across the country and Canada to anyone participated in the hydronics community. This was actually the very first one, and he made it for himself. It was a cardboard wheel that he made at home. And it was just quite selfishly, he just was tired of grabbing books and looking for formulas and all of that. And he said, I just want to make it easier when I'm doing these presentations, doing these calculations, et cetera, anything to do with hydronics. So he put together a cardboard wheel. And one day, as he's at Bell and Gossett headquarters in his office, you know, doing some work, he's in his office with this cardboard wheel, and one of the principals from B&G is walking down the hallway and just happens to stick his head in the door. And he sees this thing and he's holding it. He's like, yo, what the hell is that? We've never seen that. What do you got there? So he explained it. So they went back and I guess talking to marketing department or whatever, they said, hey, this is something we could probably pass out to the industry as a useful hydronics tool. And that's what they did years back. So his own little cardboard wheel for himself to help and make it quicker to establish in size and all of that, became this system size over the last 60 years or so. It's kind of interesting. But anyways, real quickly, the wheel is made up of 5 scales. And there are 3 on one side, 1, 2, and 3. And then on the flip side, excuse me, there'll be scale 4 and 5. In addition to this plastic wheel, there's an app. Like everything else in the world, there's an app for it, right? There's an app for this. So if you go to, say, the App Store, Apple, I think even Google have it in Android, but you just type in the Bell and Gossett, system size, or start to type it in, it will pop up right here. This particular one's from the Apple App Store, but B&G system size, it'll pop up, it'll populate. It's free to download to your iPad or your iPhone if you want it. A lot of us have over the, over X number of years that it's been available, put it on our phones. To be honest with you, I'm out in the field, like when we're not doing classes, I spend a lot of time in the field looking at problems, steam and hydronic systems, helping contractors and wholesalers and everyone that we touch throughout that chain of the hydronics market. So I'm just, I guess, a little old school, but I always have this in my job folders. It's just, I don't know, it's quick, it's referencing, but I'll have guys, they'll have it on their iPad, they'll have it on their iPhone, and that's whatever you're comfortable with. If you even want to take advantage of what it offers, but it has modernized, if you will. And they even have a Windows version that you can put on your computer. And it just, as you get into some of this, it has a lot more capabilities in terms of different fluids and temperatures or glycol makeup percentages. This is just straight water, 2 pipes. It's steel and copper. But anyways, this is the evolution, if you will, of this little wheel, which started as a cardboard wheel. So scale 1, all it's talking about is that relationship of heat transfer, BTUs per hour, and flow in gallons per minute. And when you're looking at that scale, scale 1, just a couple things to point out, but to make the numbers work within that small little area, 1 MBH is really representing 1,000 BTUs per hour. So as we start looking at it, we'll go through some examples. Just remember that that 1 is really 1,000 BTUs per hour. And then you also notice on the top part of that white band in scale 1 is temperature difference at the top, and then the symbol delta T. And it's listed from 1 degree all the way up to 200 degrees, which is pretty kind of wide. We're going to find that we typically sit within a certain range most of the times, but we'll go through some examples. And it's based on that formula we kind of talked about last week. Flow rate, we can establish flow rate once we know a load divided by some parameter. In this case here, that constant for standard water properties at 60 degrees at 500. Where is it from? 60 times 8.33, 60 times 8.34, 500. Times my delta T, my temperature drop. Temperature difference between supply and return. I keep saying temperature drop, but cooling, it's going to be a temperature rise. So either one. So there's a relationship. If I know the temperature difference and I know the BTUs, I can find the flow rate. If I know the flow rate and I can see a temperature drop that's taking place through some temperature gauges, I can establish what the load is. I can figure out calculate what the load is actually going on at that given set of circumstances if I know flow and delta T. There's that mathematical relationship that kind of works back and forth. So these are just some very simple numbers, but this is how, if you had the wheel, this is how you could interact with it. And you say, look, determine the flow required for 100,000 BTUs using a 20-degree delta T. All we're going to do is scale 1. We're going to say, okay, again, remember that 1 MBH is 1,000 BTUs. So 100 on the screen here is really 100,000 BTUs. So 100,000 BTUs, and all I want to do is I want to take that wheel, scale 1, and I want to line up the delta T. I want to find that number 20 and line it up opposite 100. And once I do, I just look in the small small white window down here where the letters GPM are in the arrow, and it will tell me the GPM. Or I can do the math formula. I could sit there and figure it out mathematically, use a calculator or whatever. But it's saying flow rate, delta T, BTUs an hour, delta T, established flow. Very simple. Take the same load. Again, these are just very small, simple, easy numbers, but take the same load, 100,000 BTUs, and say you want to design it on a different delta T, and you decide to increase that delta T and you widened it to 40 degrees. You could quickly calculate the new flow rate. And then right off the bat, which you guys probably already know intuitively, but there's this inverse relationship of flow, temperature change, and BTUs per hour. So if I increase the delta T, I reduce the flow rate. If I tighten the delta T, I increase the flow rate. So I increase or decrease depending upon how I adjust my delta T. And that will come into play later on as we get into some things. But scale one, again, it's just going through a couple of quick examples. Say I had a load of 600,000 BTUs, and I designed it on, in this case here, maybe it was a snow melt system, like in a driveway at a hospital, emergency entrance or something like that. It's very common to design snow melt systems at a 30-degree delta T. Having knowing that, line those two conditions up, what's my flow? So 600,000 BTUs, 30-degree delta T, flow rate at 40 gallons a minute. Just real quick examples. One last one. I got, let's see if I can move this without reinventing the wheel. Get this out of the way. Let me go this way, see if I can hide it. This last one here is saying, hey, I got 20 tons of cooling designed on a 10-degree delta T. 20 tons of coolant, 10-degree delta T. What's the flow rate? So real quickly, 20 tons times 12,000 BTUs per ton would give me a load of 240,000 BTUs an hour, or 240 MVH, which I could then again take that scale one, find 240, 200, 10, 20, 30, 40, line it up opposite that 10-degree temperature rise, delta T. My flow rate's just under 50. It's 48 gallons a minute. So whether it's heating or cooling, it's just a math formula. He just made it as a quick little calculator. So 1 ton of refrigeration, 12,000 BTUs per hour. Where does it come from? We always say, I got 2 tons. I got 24,000 BTUs. I got a ton of air conditioning. I got a 5-ton chiller. I got 60,000. Where does it come from? So all it is the amount of heat added to melt 2,000 pounds, a ton, of 32-degree ice and change its state to 32 degrees water over a 24-hour period, which is 288,000 BTUs per day, or 12,000 BTUs an hour. That's the reference when we say, hey, 12,000 BTUs per ton. It goes back to quite a few years ago, but melting a ton, 2,000 pounds of 32-degree ice, not changing its temperature, just changing its state from solid back to liquid. So one last thing on the scale one, we'll move on. But it's saying, hey, I'm out in the field. Now, how many times you're going to get this opportunity, I'm not sure, but just know it's available to you, and I can encounter it a lot of times out in the field. But you're at a job site and you want to know what's the actual load on the heating system while you're there. You see the water leaving the boiler plant at 180 and it's coming back at 160. So there's that 20-degree temperature drop. And you determine by checking the pressure drop across a TDV, a triple duty valve, a balancing valve that has a gauge, some ports that I can read a multimeter across it. But the point of it all is I've established that the flow rate is 600 GPM. So then the question becomes, well, what's the actual heating load? What's going on at that set of conditions? So what can we do? We take that scale one. Now we're not looking for flow rate, right? Because we already said we know what the flow rate is based on the gauge reading across that triple duty valve. So we know the flow is 600, and the delta T, you know, we didn't spell it out, but it's pretty straightforward. 180 to 160 is 20. So I line up those two factors, 600 in the small, opposite the 20-degree delta T, and what do I find? 6,000 MBH or 6 million BTUs. So under that set of conditions, 600 GPM, taking a 20-degree delta T, I'm moving, transferring, delivering 6 million BTUs. So again, it's just math, just a useful tool. Scale 2. What that's referencing is it's saying, okay, now that I've established flow rate, what size pipe do I need? And then what size pipe, what's the pressure drop of that pipe for the given flow rate that I want that pipe to support? So again, on this plastic wheel, kind of limited, it's pretty old. We'll talk about Schedule 40 steel pipe and Type L copper tubing. As you get into either that app or some of the software that's available, obviously it opens up to PEX piping, perhaps PVC, other scheduled pipe, other type copper. But for our example here, it's going to reference flow rate based on these two types of pipe. There's going to be friction loss stated. Did I just do that? You did that, Willie. Oh, all of a sudden it just popped up on the screen that I had everyone that was participating. But anyways, so we're going to have friction loss stated in two terms: milli-inches per foot. We're going to talk about it right now for the next 10 seconds, and we're never going to say it again. It was very common, again, 70 years ago, converting gravity to forced circulation. The pipe size was so huge, the pressure drop was so low, they had to come up with a measurement that kind of made sense. It wasn't in feet per 100 feet, it was in milli-inches. Moving forward from this conversation forward, and what you will experience and design and see out in the field, it's going to be in feet per 100 feet of pipe is going to be the industry standard. And this scale will reference that. So feet per 100 feet establishes the rate of pipe friction loss as a foot head of energy loss per 100 feet of pipe. So scale 2. We got this, like I call it like a triangle, this white band or this white triangle here. And in it, you're going to see these two arrows, Type L copper and iron pipe. And whenever you're selected, and you're trying to find what size pipe I need, you're going to use this band right here, this white band that kind of moves from left to right or right to left, but it says GPM flow. You want to make sure that whenever you're saying, hey, I think I want to use this size pipe, let me see if it works, just make sure the arrow is lined up opposite that particular either iron pipe or copper pipe. And then from there, you can start to read and say, yeah, here's a friction loss. Here it's going to work or it's not going to work. And we want to reference it on the top side of that scale is piping friction loss feet per 100 feet of pipe, which is this guy right here. We don't need to reference that lower bottom part, which is the milli-inches. So on that first example we did on scale 1, talking about trying to establish a flow rate, I got 100,000 BTUs to 20-degree delta T. We said, hey, 10 GPM. So I take scale 2 and I say, okay, what size pipe do I need? The way I do it is I find that 10 GPM, which is in that white band, and I just rotate the wheel, right? Until, in this case here, let's say we're using copper pipe. I want to find what size pipe kind of falls right here within this white triangle. And so as you start, typically you're going to start from the smallest to the largest size. Why? Why wouldn't you start from the largest down? A lot of times it's just economics, right? Why spend more than you need to in terms of buying a larger diameter pipe and larger fittings? But at the same time, you don't want to use pipe that's too small because it's going to create excessive pressure drop, which is going to affect pump selection. And then also another factor we'll get into in scale 3, you can get into velocity. How fast is that moving feet per second? So there's some industry standards we want to kind of stay within the guardrail. So it's going from smallest to largest. The first size pipe that I can line up this arrow, in this case here, copper tube, is 1.25 inches, where I can find that 10 GPM somewhere within that white band. And so when I line it up, all I do is I read straight down. I say, here's 10, here's my GPM, read straight up. This is going to tell me the friction loss in feet per 100 feet of pipe. So Our answer here is 2.6 feet of pressure drop head loss for every 100 feet of pipe when you're circulating 10 GPM, 10 gallons a minute through 1.25 inch copper pipe. So if I had 1,000 feet, 50 feet, whatever that number is, 2.6 times however many feet. That's my frictional resistance to move that GPM through that diameter pipe. Another quick second problem was, hey, if I doubled the delta T and went to 40 degrees, my flow rate cut in half for that 100,000 went to 5. Again, just scrolling through, in this case here, the smallest diameter pipe where I can find that 5 and that white is 1 inch copper. I find it, I read straight up, it's just to the right of that 2, so it's 1.9 per 100 feet, just establishing frictional resistance. Here's just a quick example. It says, look, determine what size pipe I need for 70 gallons a minute in a typical hydronic system. What's the BTU capacity of 70 gallons a minute? The first question you want to ask me is say, hey, George, at what delta T? Because that will impact what your answer should be. But if we stay with what we're talking about, said industry standards, 20-degree delta T, it's a heating application. 70 GPM would be how many BTUs? What scale are we going to reference to establish BTUs based on flow rate? Scale 1, right? Scale 1. And all I'm going to do is I'm going to say, hey, if I'm going to do a typical 20-degree delta T and I have a flow rate of 70, so I don't need to find the GPM. I'm already going to line up the GPM in scale 1. And I'm going to look up on the big scale and I'm going to say, hey, at an opposite 20-degree delta T, it's this many thousands of BTUs per hour. It should be 700,000, right? Or I could just take 70 times 10,000. 500 times 20 is 10,000 times my flow rate. There's my BTUs. So anyways, now what size pipe? Well, in this case here, you actually have two answers. If you go with the smallest size pipe in iron first, the first one you come across is 2.5 inch. So I find 70, it falls within that white triangle. I find 70, I read straight up. It says about 3.5 feet of pressure drop for every 100 feet of pipe. Okay. If I continue on, it's one of those examples where actually two pipe sizes kind of fall within that category. One's a little bigger, the next size up is 3 inch. It's still within that white triangle. And then again, read straight up. Now it's about 1.2. So some of the things you might consider would be upfront cost. Buying 2.5 inch pipe and fittings is a certain price. If I bump it up to 3 inch, it's going to be 3, plus. It's going to be a little more money, right? But then if I maybe look at the life cycle cost of operating the pumps and the motors and the KW that I'm using on a certain system with lower pressure drop over X number of hundreds of thousands of feet, maybe that's something I want to measure or want to consider. That maybe I do go 3 inch. But the point of this quick exercise is, look at, I use scale 2, find which size pipe, make sure you're lining it up opposite the pipe that you want on that arrow, and then just find it in the wheel, read straight up on the scale, that's your pressure drop, and it's per 100 feet. Scale 3, it's the only time when you're using this, if you ever choose to use it after you walk out of here tonight, is where the two scales work together. Like when you use scale 1, once you get that answer, it doesn't line up. They're independent of each other. But this is the one time on this wheel where scale 2 and scale 3 work together. So scale 3 is talking about establishing that water velocity in feet per second. How fast is it moving? Scale 2 tells me the pressure drop for every 100 feet of pipe. Scale 3 says, what's my velocity? How quick am I moving through that pipe? And there's kind of a high and a low. Too low, and you might allow entrained air bubbles that might be out in your system, and the buoyancy in those bubbles might be greater than the velocity if the feet per second is too low. So on the low side of the industry standards, you don't want to be any lower than 1.5 to 2 feet per second. That will ensure any air out in the system the velocity of the water can bring it back to your mechanical room, pass it through your air separating device, and get rid of it. On the maximum side, there's a couple of different standards, but if noise, like in an apartment building, a condo, an office space, a hospital, where noise is a concern, now you're talking somewhere in the range of around 5 feet per second as a high. When you're in a commercial setting, a manufacturing setting where noise, there are other issues going on with noise, so noise is not a concern. You're not, in a classroom or in a doctor's office or something like that. Then you're getting into erosion, corrosion. So now a higher feet per second, typically in that 6 to 8, 8 being the high side, feet per second. So what's my application? And then what is my high side of my feet per second? Noise, right around 5. Noise is not a concern. Try not to exceed that 8 feet per second. And that's just a quick picture of velocity in air bubbles. So it's the one time, like I said, scale 3 works with scale 2. And as a quick example, we'll say, hey, let's see here, 70 gallons a minute. In this case here, I think we lined it up opposite the 2.5-inch iron pipe, and I found the 70. Now what I want to do is I want to intersect my 70 down here on scale 3 without moving the wheel. Just read it. What is it? Where does it intersect? It's about 4.4, 4.5 feet per second. That's below the 5. That'd be a good. So it's almost like a check. I find the flow rate, pipe size, pressure drop without touching the wheel. Just, okay, it's within good industry standards. Move on. It's a good selection. But you've established that it's not too noisy, not too slow. A couple quick examples would be that we did it earlier with the 1.25-inch copper pipe for the 10 GPM. I found my pressure drop, scale 2, quickly glanced down to scale 3, 10 GPM. Where does it intersect? Right about 2.4. So again, not too slow. It's above that 1.5 to 2, not too high. It's a good selection. And again, just the 5 gallons a minute. Quick example, they say, hey, what's the velocity of 1,600 GPM flowing through an 8-inch diameter pipe? So it's going to be 8-inch iron, and I've got 1,600 GPM moving through this distribution pipe. So I'm going to line up 8-inch on scale 2, and then I just want to glance down to scale 3 and find the flow rate of 1,600. So I have 1,500, then I have 2,000. So just north of 1,500 to 1,600, and where it intersects is over 8. It's about 9.5 feet per second or so. That would be considered aggressive, probably bordering on erosion. So I don't want to do that. I want to move to the next size pipe, which in this case here, 8 is the next size pipe up is going to be my 10-inch diameter pipe. Now I, again, line it up, glance down to scale 3, find my flow rate, 1,500, 1,600. I'm right around 6.1, 6.2. I'm fine from an erosion standpoint. I'm below that 8. Yes. Well, if it's noise, I don't want to be typically higher than about 5 feet per second. And I don't want to be lower. And as far as an answer, in the catalog, one of the manuals, I think yeah, that's true. Yeah. Number of hours, right? If for noise consideration, correct? Right. Scale 4, I'm just going to move through this real quickly because scale 4 is when you think about when this thing first came out in probably the late 50s, early 60s, there wasn't a lot of calculators kicking around the industry. Every phone, every watch, everything you own has a calculator. It's nothing. It's nothing to even consider or think about. But years ago, he made the scale 4 to just simply be a calculator. And the point of it all was on scale 2, we just figured out, okay, I know my flow. I picked the right size pipe. Here's my pressure drop per 100 feet. Scale 4 would say, well, how many feet do you have? Do you have 2,000? Do you have 400 feet? Do you have 100? What do you have? And you'd kind of line up a couple of sets of conditions, and it would multiply it out behind the scenes and say, hey, here's your total pressure drop. Not that useful or needed today because we've got calculators. We can quickly figure it out. But that was what scale 4, why it was developed. And so what it's saying here is determines the required pump head based on the resistance per unit and what's the total piping circuit length. How long? How big is that system? To use scale for 4, the first thing you want to calculate, though, is what they refer to as that TEL. And what they're referring to is fittings. So in addition to straight run of pipe, you got an elbow, you got a T, you got a 45 or whatever. And you're supposed to account for those because those fittings have a resistance or a TEL. They might say that, you know, a fitting, 2-inch elbow or 4-inch, whatever, that might represent 10, 15, 20 feet of pipe. I got to account for that and add it to my straight run of pipe so that I have my TEL, my total equivalent length. So we'll go with a quick, go through a quick example, but industry standards, rule of thumb, pretty safe. Take that length of run and add 50% to the straight run, and that becomes my TEL. It's a quick rule of thumb, but it's, I got 200 feet of straight run of pipe. Instead of sitting there trying to figure, calculate all the fittings, times it by 1.5, okay, 300 feet. That's an easy way of accounting for. On the back side of the sheet, the casing, if you will, they actually had labeled, you know, years ago, the cast iron and steel screwed fittings or flanged fittings in different diameters, you know, from, I think it's actually, where did I put my glasses? In my hands, that's great. A 1/4 inch all the way up to 24-inch diameter. So some pretty aggressive sizes. But anyways, we typically day to day, you're not gonna sit down and count it. Half the time when we're out in the field, half the piping's behind walls, so it's already existing. You know, you can't even find it. When you're sitting down designing and you're using software, it's probably going to already calculate all the fittings that you've included when you've laid out your system. But it's just giving us a quick example here. A 90-degree elbow, cast iron, 4-inch diameter, has the equivalent length of 11 feet. It's just, it's a printed chart. So again, scale 4, you know, whatever your length of run is, add 50%, times it by 1.5 becomes your TEL. So on that first example, just real quickly, if I had that flow rate of 10 gallons a minute flowing through 1.25 inch copper pipe, and I had 200 feet of it, what I would say is, okay, 200 times that 1.5 gives me a TEL of 300 feet. My pressure drop was about 2.6 per 100 feet was the example we used. So what I'm doing here is I'm finding my length of run in the white band. I'm lining it up opposite the pressure drop I established in scale 2, 2.6. And all I do is I glance down here and it does the calculation. And it says, hey, your total pressure drop for 10 gallons a minute through 300 feet TEL of 1.25 inch is just about 7.5, 7.6 feet ahead. It did a math formula for it. If we jump to that 70 gallon a minute, excuse me, what do we got going on here? 2-inch. What's the total pressure drop in a pipe with a TEL of 130 feet and a flow rate of 200 gallons a minute? Now it's asking us to use the wheel and saying, hey, total pressure drop in a pipe with a TEL. If I've got the TEL of 130, do I need to account for the fittings? No, it's already given it to us. It said, hey, I've included it. It's my TEL is 130. And at a flow rate of 200 gallons a minute, if I'm using scale 2 and I establish the pipe size needs to be 4-inch, 200 GPM, it's just about 2.3 per 100. Flip it over to scale 4. I line it up opposite 130 feet, 2.4. My total pressure drop is about 3 feet on scale 4. That's how you'd read it. This last scale, scale 5, is it really kind of relates to that expression, we talked about that system curve. How that system curve is established, that relationship of flow and the change in flow and the corresponding change in head loss in that system really is the basis of how scale 5 is established and how it works. So it can be used for a couple different things, and one of them would be this: establishing that if I have a known flow rate and a known pressure drop, I can then calculate any other corresponding head loss if I pick a different flow rate. So real quickly, a chiller manufacturer says, hey, at 100 gallons a minute going through my barrel, a chiller barrel, it will experience a 12-foot pressure drop. That's published in that chiller manufacturer's catalog. And the question is, hey, if I try to bump up the flow through that chiller to a flow rate of 150 gallons a minute, what's the new pressure drop through that chiller? Because it's going to be different than at 100, right? You're putting more flow rate through the same given diameter. So you could sit there and you can do this little calculation with your calculator if you wanted to. You could do a math formula. Or you could just take scale 5 and say, hey, what do I know? Well, I know that at a flow rate of 100 GPM, the pressure drop is 12 feet. So on scale 5, one of the things you want to be aware of on this wheel is the top side of the scale is listed in feet of head, and then the bottom side is listed in PSI, pounds per square inch, that we started talking about those terms last week. So in this case here, the chiller manufacturer said, hey, my pressure drop is in feet of head. So 100 opposite 12 feet ahead. And then what happens is once you line that up, don't touch the wheel, don't move it. Just glance, find the new flow rate. In this case here, 100, read it straight up. What's the pressure drop? About 25, 26, 27 feet ahead. You just want to account for that, because if you're going to increase that flow rate through that chiller, you got to make sure that that pump that you have pumping that chiller can overcome that resistance. That's all. So there's a relationship. You change the flow, what's the new pressure drop? It's a formula. Scale 5 kind of is set up that way. A closed system has a flow rate of 200 gallons a minute and a head loss of 30 feet. I just want to plot the system curve. I want to see what that system curve is relative to the pump I'm going to select. So again, this is my known set of conditions, 200 opposite 30 feet. So then I just arbitrarily picked some other flows, and I can find out just real quick, looking at the glancing at that scale 5, what are the new pressure drops? So at 100 gallons a minute, I read straight up, it's about 7.5 feet ahead. 300 gallons a minute, about just over 65, it's about 67 feet. So I can pick those numbers and I can plot those on a curve, or the software that we're going to use, or that we do use, does it for us. But that's where that curve's coming from, is that simple relationship that exists between flow, change the flow, what's the known pressure drop, what's the new corresponding pressure drop in that closed loop. And the one last thing is you can use scale 5 to help select control valves based on the valve's C sub V, its valve coefficient, its performance, its capacity rating, which every valve that's manufactured has a corresponding number, a C sub V number. And scale 5 again follows that. So what is CV? Just real quickly start there. What is a C sub V? It's the flow in gallons per minute across a valve that will cause a 1 pound pressure drop, a 1 pound pressure differential across that valve. So the manufacturer of the valve makes this valve, control valve, Johnson Controls, Honeywell, Barber Coleman, Tecma, three-way mix, whatever it is, they are a ball valve. They all have a C sub V rating. And when that valve is manufactured, they'll test it. They'll say, hey, what is the CV of this valve? When you move a certain flow rate, what's the corresponding pressure drop? I need to know that. Control valves, zone valves, regulating valves. So kind of a picture speaks 1,000 words. I have this valve. what's the flow in GPM that's going to cause this 1 pound pressure drop? So I have a certain pressure on one side, I have 1 pound less on the outlet. That becomes that particular valve's CV rating, whatever that GPM is. And then knowing the relationship that we talked a little bit about last week, the relationship, how you can convert PSI, pounds per square inch, to feet ahead, or conversely, feet ahead to PSI. When you look at scale 5, I don't know if we go back real quick. Yeah, right here, here's a highlight. But just as we, just looking at scale 5, forget these numbers and all of that. Just notice where it says the letter C and small letter V, CV. On the feet ahead side, it's highlighted, marked at 2.3. Read straight down on the PSI side, and it's labeled at 1 PSI. So the CV is the flow rate in gallons a minute that creates a 1 pound pressure drop. All valve manufacturers, all valves have this rating. And scale 5 just acknowledges that. And you can use it to help establish select and control valve. Let's see here. So typically what would happen as far as a manufacturer who manufactures valves and they want to test it, they're going to say, hey, water level remains constant at 2.31 feet above the valve inlet to maintain a 1 pound inlet pressure. So I got this vessel 2.131 feet above it. It's full, it maintains. That flow is going across that valve to 0, dumping into this open vessel. The volume of water flowing for 1 minute can be weighed to determine the GPM. So that's how they'll test the valve. And they'll say, hey, this flow rate here after this 1 minute caused this 1 pound 1 to 0. That becomes the CV rating of the valve. So all your control valves, you're out there and you got zone valves, you got regulators. You look in one of the columns will be the CV. That's how they established it. They figured out what the flow rate was in gallons per minute that created a 1 pound pressure drop between its inlet and its outlet. So real quickly, control valve is to be selected. So you're specifying a control valve on, say, a chilled water coil. And I want to make sure that I have a 3 pound pressure drop across that control valve for maybe some type of control valve authority, which is another whole subject we'll talk later maybe. But a control valve is to be selected for a 3 pound pressure drop when there's a flow rate of 2.9 gallons a minute going into that coil, that chilled water coil. So then you say, okay, well, what's the CV? What would the CV rating of that valve have to be to meet those set of conditions? And again, using scale 5, I have a set of known conditions. What are they? At 3 PSI, right? I want a flow rate of 2.9 gallons a minute. So on scale 5, reading the PSI on the bottom side, here's 3, line it up. So rotate that wheel and that band so my GPM is 2.9. Those are your known conditions. We just stated it. Then all you do is you kind of read back and you say, okay, where's the CV? What's it lined up opposite? That becomes the GPM, which is the CV rating for the valve that you're going to buy to meet that set of conditions. So in this case here, a valve that has a C sub V of 1.7, right? So it manufacturer says, hey, I create a 1 pound pressure drop when I have a flow rate of 1.7. You take that valve, you put it into your chilled water application on this fan coil, and you say, hey, I'm going to be pumping 2.9 gallons a minute through that coil. I want that valve to offer me a 3 pound pressure drop. That valve will when it has a CV of 1.9. That's that relationship, flow and head. Change the flow, change the corresponding pressure drop. So if I know the CV, I can create this. If I know what my known conditions, I can work backwards and establish what the required CV would be. Yes, Tom? At this, yes, this scale, right. Yep. Yes, it will get into different percentages of glycol as well as the online. as well as even into some valve manufacturers, and they'll take this, you know, even a step further perhaps. But at the end of the day, the main thing is just recognize that mathematical relationship about changing the flow, corresponding pressure drop, a squared relationship. It kind of applies all the way through a lot of our closed loop hydronic systems. We'll jump into the subject. We'll probably bump up against a little bit of stop for a bite to eat or whatever, then we'll get back into it, and then we'll continue to move forward. But variable speed pumping, it's an everyday thing. It happens in all hydronic systems, heating, cooling, anything over. I think ASHRAE dictates, is it 2 horsepower or 3 horsepower will if a pump's going into a heating or cooling application with I think it's maybe. Yeah, it's going to require a drive on that, some type of drive. 2 horse, 3 horse, I think it is. Yeah. But anyway, so it's very common. It's going to happen all the time, and it has been going on. Just want to understand the why. Why are we doing it? So a couple of just silly little old pictures, but it kind of leads up to what are we doing today? As systems grew, hydronic systems grew, and before VFDs, before they were developed or required or said, hey, do we even want to go in this direction? You could have had a fairly good sized system with a constant speed pump and then a bunch of terminal units controlled with a 2-way valve. Just space temperature, perhaps, saying, hey, open or close the valve. It might not have been modular, it might have been simply open or close. And they were just glad they had that, you know, back years ago. And then they quickly started realizing as that, you know, set of conditions. So in this case here, maybe I had a set of conditions where I was pumping 1100 GPM and the system was offering me a total pressure drop of about 100 feet. So when I went and selected this distribution pump, those were the set of conditions. When everything's calling, I got to be moving 1100 GPM and I got to overcome 100 feet ahead. And within that, these terminal units and this control valve, there's going to be a certain control valve pressure drop to support the individual terminal units. Now there's 3 of them. There could be 300 of them, you know, whatever that number is. As the control valves close, now why do they close? Well, the space temperature within the area that they're providing the cooling, in this case if it's chilled water, are satisfied. Valve closes. Don't want to freeze the place, just space conditioning. But it's a constant speed pump. At the time, there was no variable frequency drives to regulate the operation, the speed of the pump. So the pump backs up on its curve. It has to, because there are less zones open because the valves are starting to close. So the pump does what it has to do and it stays on its curve, has to operate on the curve somewhere, but it just backs up. And in doing so, where we might have had a control valve, you know, when all the zones are calling, trying to overcome 20 foot of pressure drop, that might be a dedicated or a design, a control valve pressure drop within the system of 20 feet at 1100 GPM. As I start to back up, and in this case here, maybe I cut the flow rate in half and I'm only at 550 gallons a minute. Look at the pressure drop, the head absorbed by the control valve. Because this pump's backing up on its curve, I don't have 20 feet, you know, for every individual. I'm producing upwards of 90 feet of pressure differential for the remaining 550 gallons a minute. So these remaining control valves that are now, maybe they're starting to try to control, close, and they're trying to close against a substantially higher pressure differential, because they're the only ones remaining. The pump's doing its job. It's backing up on its curve. It's not out here providing that 20 feet. It's backed way up. They might be seeing 90 feet of pressure differential, to the point where some of the valves that are closed might be forced open. And they would have discovered this, you know, years ago, because the head differential, the valve's closing ability relative to this head energy, this excessive head energy that exists. So this is as the industry was, you know, evolving, and all of a sudden they'd fix one thing and solve something and create another and say, hey, we got to address this. One of the first things they did is they went to this. What's the difference between this drawing and this drawing? three-way valve, right? And so on the three-way valve, now I have what? 2 inlets and 1 outlet. So I can come out through the terminal unit and pass the outlet port into my return. I can go through the bypass. Maybe if it's a modulating valve, I might do a little bit of both, or maybe it's just a 2-position three-way valve, open or close. What was the reason for doing that originally? What were they trying to accomplish with that three-way valve versus what they were contending with a constant speed, no variable frequency drive pump? Say it again. I didn't. Minimize. Yeah, like in theory, if it's done right, there is no head creep. It's always 20 feet. So what would happen is, why is that bypass valve, balance valve there? What's he trying to simulate? If I bypass, I want to make sure that that valve acts as if I'm going through the terminal unit in the control valve, so that the pump doesn't see a difference. The space temperature sees a difference because it doesn't or in this case, overcool the room. It will bypass. And so they'd have these balance valves there to balance, so that they would create the pressure drop as if the flow was going through the terminal and the control valve. Instead, it's just going through the bypass and the control valve. So it never saw this backing up on the curve. So the remaining control valves never saw this excess of head. But what's the downside to this? Pump power wasted, right? The control valves operation was much smoother, but you're still consuming a tremendous amount of energy, kW. There was no change in speed, so there was no change in consumption of energy. It just allowed the control valves to, operate more smoothly than this way with these two-way valves. So the industry again said, okay, there's got to be something better than this. We got to, and it evolved. And so it evolved into getting into VFDs, what we want to talk about, variable frequency drive. And what they were applying to get into this was what we've just talked about, the pump affinity laws, the relationship about that prediction of the change in flow, the change in head. And then the other interesting thing would be horsepower, the energy needed. So there's a mathematical relationship. So you get into, if the pump capacity, it will change or it will vary directly, right? And it's saying as you change the flow, there's a direct relationship as you change that flow, what it will be. So if you change the speed or you change the diameter of the impeller, there's a direct correspondence. With the head, just like we've talked about a little earlier, the pump head varies as the square of the speed or impeller diameter. So when we're getting into VFDs, we're not changing the diameter of the impeller, but we're changing the RPMs of the motor. How fast is it spinning? Speed control. So if I change that, I have a squared relationship. And then lastly, the brake horsepower varies as a cubed relationship of the speed change or impeller diameter, but we're going to talk about speed, RPMs with VFDs. So you change the flow, it's a direct relationship. You change the head, it's a squared relationship. You change the speed and you affect the horsepower, the brake horsepower, by a cubed relationship. So you start applying all of that. Cut the flow in half, the flow is in half. The head is a quartered and the horsepower is an eighth of what it was. So if you have that 75, 50, 100 horsepower pump, yes. I'm sorry, David. No. How's that for a quick answer? This pump isn't shutting down. So, as we get into variable speed, you're going to have, we'll talk about it. There's always going to be a minimum. Either the pump manufacturer says, hey, I got a minimum flow. You can't just bring me down to nothing. And then I have a control valve that's got a control head that I got to contend with. So I always got to provide a certain pressure differential from my drive on my variable speed pump to support that pressure drop of that control valve. So if I don't have flow, I guess go back to this. if I have flow, and maybe it's only supporting this last terminal unit, or whatever the case may be, and these two are closed. And then all of a sudden, the temperature, space temperature requires that valve to reopen. Say it's not modulating, it's just two-way, open or closed. If I've already got flow in that main running constantly, I mean, other than the time frame or the difference to get that heated water or that chilled water to that coil, I'm not going to say it's not immeasurable. I'm sure there's a measurable, but it's not enough of a difference, I think, David, to, I mean, if you're into manufacturing and some kind of precision, but if you're talking space, comfort, temperature in a dorm room, classroom, office space, no, it's not enough of a difference to notice performance in the space, heating or cooling. I don't know if that answers your question. We could talk a little bit in more detail, once we take a break or whatever. But because the industry itself, they've actually banned that. You can't use a three-way valve because you don't have any reason to have speed change. So you're constantly wasting energy. They want that speed control to reduce the consumption if the load isn't there, whether it's heating or cooling. So they're driving for energy costs. Get that 100 horsepower, ramp it down as low as the system only needs. Experience the savings on the energy consumption, but also not just be wasting that energy and creating issues with control valves in terms of high pressure differential that it would see as it backed up on its curve. So we talk about this, the pump affinity laws, and we just apply it to variable speed pump. Change the speed, change the flow, squared relationship, change the head, cubed relationship, change the brake horsepower. And here is a quick example, if you will, changing that. And again, just kind of spelling it out in a different format. But here, if we just jump down real quickly, the speed of the pump goes from 100% to cut it in half, 50%. And the flow is cut in half. The head required would be a quarter. And the horsepower required would be an eighth, or 13%. So there's a pretty, that was what drove, and what the utilities, even today, they're very active in providing incentives for any remaining equipment that's out in the field that is an induction motor that doesn't have speed control. They have all kinds of incentives out there to get a drive on that fan, or that, in this case, we're talking hydronics, that pump that's pumping hot water or chilled water around a building of some sort, commercial building. So they see that benefit, and it's real. We've been doing it for 40 years or so, or more. And to the point where ASHRAE 90.1, talks about, what they refer to, I guess, a prescriptive compliance path. But hot water distribution, 3 or more control valves designed to either modulate or open close as a function of load shall be designed for variable fluid flow and shall be capable of and configured to reduce pump flow rates to no more than the larger of 25% of design or the minimum flow rate required by the equipment manufacturer. Further on in that little paragraph, it'll say whether it be individual or parallel pumping for heating or chilled water with a horsepower of the motor, of the nameplate horsepower of the motor or combined is greater than 2 horse, you're going to have a drive to be compliant with this standard, this energy standard. So it's everywhere, and you're going to design, as a matter of fact, and I'm sure the firms that you're at right now, they're already doing that, and you guys might be doing it already. But that's the reason, is it's energy savings. It's taking advantage of that pump affinity law relationship. Change the flow, cut it in half. Change the required head loss, it's quartered, and the cubed of the power consumption, is that cubed relationship. So just a quick drawing of what you might see today. Primary, secondary chiller pumps, they might be a fixed speed or variable speed on the chillers, but then you're going to have these drives that are going to control your distribution that are now going to your terminal units with these 2-way control valves. And in this case here, they're showing maybe some type of remote transmitter, pressure sensor transmitter that's maintaining a certain design, flow and head of this one. And this one thing here could be this one terminal unit. It could be one dormitory. It could be one building within several buildings of a hospital campus. It could be, a lot of different things. But we're measuring that pressure differential. We're feeding back saying, hey, as long as we maintain this minimum 20 feet, 25 feet, whatever that number is, we don't need that full capacity of that pump, because not all of my terminals, the load of the building isn't there. It's not all calling. It's starting to build up, back that speed of that RPM of that pump down through that drive. That's what's happening. It happens every day throughout all of these heating and cooling systems. And here's, again, just a little mathematical or graphical chart, but what it's trying to talk about is I've got percentage of flow, horsepower draw, and percentage of head. At 100% flow, 100% horsepower, 100% head, here's my relation, this is how it all kind of interacts. As I start to reduce, and in this case here, my flow drops down to a half. My head is about a quarter, 25 feet of that 100 or so, and my horsepower is an eighth, or about 13% of what that original horsepower draw was at design conditions. So again, just kind of repeating. What I just want to show here is what they're just talking about here is when you go to select some of these pumps and you're selecting them in that variable speed mode, as opposed to a constant speed criteria, you have that selection in the software. It's going to kind of print out or show us, the efficiencies, if you will, all this pump all the way through as you're changing that speed from maybe a maximum of, I can't read it, but 1770, 1780, 1772, all the way down to what that minimum RPM is and how close it stays to that BEP, that best efficiency. So the pump can, as it's changing its speed, it can maintain some pretty high efficiency all the way through that reduction. So you're not hurting the efficiency of the pump with this drive. It's all about the selection and then looking at the software to say, okay, how does it operate from that maximum design condition all the way through? And what am I showing here? What's this line here that's moving from the left up to the right? What would that be called? System curve. That's the system curve, and it's going to intersect, in this case here, that full speed, full RPM, design conditions, flow and head. And then as those valves close and those pressure sensors sense that change in pressure and they want to back that pump down, they're going to change the speed. Here's the intersection through these different changes in RPMs to where that pump is operating and what the efficiency will be all the way through. What I think I want to do, Will, is maybe we take a break right now. I think supper's already arrived. I think, Sherry, I don't know if you just want to check. But if we could probably just take like a 15-minute break. Everything's ready? Lobster tails, butter's drawn? Hope you guys like lobster. But anyways, and for everyone that's listening remotely, 5:30, we'll get together at 5:45. We'll get going. Okay, we're going to get going here. Just kind of pressing on with just finishing up a little bit on the variable speed. But I just wanted to make you aware, just as another source of information, if you're really motivated and taking a deep dive. But in that engineering catalog, one of the TEH manuals is very specific about this variable speed, variable volume pumping. So as a subject matter, it can get pretty deep, so depending upon if you want to just touch the edges, or if you want to really dive in, it's some pretty good, and typical with a lot of these manuals, it has nothing to do with the product. It's just the application. What are you doing? And how do you do it and how it impacts, et cetera. So as you're kind of moving along, let's see here. Sometimes you get into like control strategy of your VFDs. How are you controlling the pump? So they might reference it as like curve control, because the curve is your RPMs, how fast you speed, and you're moving your curve accordingly based on system conditions. So there's different ways, but what they're kind of showing here is maybe it might be something that on board the pump itself. I forget what they even call it. What is it, the ISTS or the onboard control as opposed to remote sensors. But where you're getting into the IT built on board, right? Okay. But what are you doing? You're monitoring the motor power and the torque change, differential pressure across the pump. You can be measuring flow at the pump outlet. So you're just going to have a couple of different pieces of feedback. And sometimes it's one manufacturer offers different ways of getting there. And then sometimes manufacturers have certain ways. And so whatever you're comfortable with or what you have, the most success with or whatever the case may be. But you got to have some information to feed back to say, hey, system conditions are changing. Speed should change. Speed control should be implemented. So some of the applications with this factory generated pump performance map, if you will, where they're mapping out the curve or the potential curve of that pump. Maybe where zones may be equally loaded, where the hot water zones, maybe you're not having that full-blown DDC system. And then a lot of retrofit systems, existing systems that they want to see that energy upgrade, where you're putting in this pump and or this style, and you want to introduce energy savings, you want to introduce variable speed, with maybe not getting remotely out into the building. You can just reference what's taking place at the pump relative to how that's being impacted by what's taking place in the system. So it's one of the strategies. Establishing key input values. You got a control curve, the performance curve. So you got a set of conditions here: 1115 GPM at 80 feet ahead. That's what these pumps are responsible for feeding, a building, a plant, a campus, whatever the case may be. And we're going to have some information feeding back to this drive, this building control to control the frequency, the variable frequency of the operation of those motors. Back here, you probably have in your boilers or your chillers, you might have constant speed or constant volume on the production side. But then once you get out into the distribution or the secondary loop, if you will, now we're going to introduce some variable speed based on loads changing, control valves opening and closing. And then what happens is you start getting into you're going to have a control circuit pressure drop, and then you're going to have distribution on the supply and the return side pressure drop. And that becomes variable, that pressure drop, that's based on 1,115 gallons a minute going through the system. As these valves start to do their job reacting to system conditions or environmental conditions in their space, now I don't have that flow. I'm not going to have this. It's going to be a variable head loss. But I still might want to have a control circuit pressure drop, like a fixed, hey, I want to maintain a 24 feet, a 30 feet, or whatever the number is across a particular circuit or terminal unit or building, depending upon the scope. And that information, that might not be variable, but the distribution piping pressure drop will become variable as we start changing flow by changing speed. And then the corresponding reduction in head, and more importantly, the corresponding cubed reduction in required horsepower. So we're just looking at a printout, if you will, of a commercial pump, a 5EB with a variable speed curve. And you'll notice that it's not starting at 0. So in this case here, we've got 1,115 gallons a minute at 80 feet ahead, which is what was kind of stated back here. Those were the conditions. So I'm looking at the curve, but it's not starting at 0. And that's because what they're saying here, is I've got this control circuit or this control valve circuit that I want to maintain a minimum of 24 feet across that circuit. So when I go to build my system curve, or when the software selection, you're plugging this in. You're saying, hey, the total pressure drop is going to be 80 feet, but my control curve and my control pressure drop is going to be 24 feet. So it's starting its system curve, not at 0, but at 24, and working its way up its system curve, or working its way back down, I should say. So the total design pump head's 80 feet, but the branch loss or head loss is 24 feet of that 80. And then the variable, which would be this guy here, is the 28 and 28 is 56 feet. That's your distribution piping that's going to see that change in flow, which means the change in head loss. And so these are kind of the inputs that are going to take place when we're designing or selecting and setting up our control, our variable frequency drive control. So again, here's that, we keep coming back to that system curve. We keep, beating on it or hopping on it, but it's that relationship. This is the system conditions. Now you notice that we went from 80 to 56 because the 24 we want permanent. We want that as our control head, our pressure drop across our control circuit, that 24 feet. So the software, the computer's automatically selecting or creating that curve based on these conditions, based on this design that we know is accurate. So really that curve, kind of that variable head loss, because of the 24 feet, we take that system curve and shift it up, or the computer does, the software does. And so it's going to vary from that design RPM, and it's going to play with that speed or reduce that speed as a result or a response to system conditions that are changing, that are lightening the load, if you will.
Versus a three-way. Is there any reason why you would put a VFD on the primary? I know it says a constant speed.
Yep.
But yeah, those pumps in
Yeah.
there, does that make sense to do it there? I
Yes.
understand that part.
Yes,
Yes,
it can. Yes, we're
We're
going to
gonna
get into that. Actually,
Okay.
we're going to move right into that. And we'll get into the kind of the ECM pumps. It's just an example, David. But if you have a boiler that, just for an example, we're showing boilers and chillers. But a quick example of the boiler would be if it was not an on-off boiler, 1 million BTUs, 0 BTUs, but it was a modulating, so it could change its firing rate, maybe based on outdoor temperature, indoor conditions, whatever. And I had a fixed flow pump. And as I'm starting to reduce my BTUs of output of my boiler, but I still have this pretty high flow rate, which is needed at full fire, but not at reduced fire, I would really start to tighten the delta T across that boiler plant. So if I say I have 1 million BTUs and I got 100 gallons a minute, what's the delta T? Well, we can do the math. We can take the system size. We can say, hey, George, tell me at the end of the day, it's 20-degree delta T reflects 100 GPM. So now the boiler is a condensing or modulating. It can change its firing rate, and it starts to downfire, or it might have a turn down ratio. So maybe it's a 10-to-1. So it could go from 1 million down to 100,000 BTUs. And that's okay. It's not hurting it. It's just responding to the set of conditions. If I keep that at 100 GPM, I'm probably going to end up with, I don't know the math real quickly off the top of my head, but probably 4 degrees delta T across that boiler plant, that heat exchanger. That could lead to some short cycling of the device, the firing, that component. So there's some logic there that says, hey, maybe I change that flow rate to maybe fall more in line with the output, the firing of that boiler, to maintain a delta T across the heat exchanger here of, say, 20 degrees. So I could ramp that pump. And then what would happen is I'd need to have some intelligence, maybe on board the plant or some third party, that could influence the speed of this pump to reflect the firing rate. And it's not that it's getting into the actual firing, it's looking at the delta T across the heat exchanger. So it's slowing its flow to maintain that 20 degrees. So in theory, I could take a pump, maybe go from 100 gallons a minute down to 10 GPM, or somewhere in that range. So there are examples and there are reasons that we might want to do that. And it's not, it wouldn't be like out here, we're not chasing delta T. Typically, it's pressure differential, it's valves that are closing. Here, there are no valves opening and closing. It's a fixed, but it might be a variable firing rate, so BTU output. So in this example, I can use maybe delta T as my piece of information to influence my GPM through speed control of that pump. Yep. 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 Yeah. It could be as simple as on off. You could take like what the example I'm going to get into a little bit later on. A lot of the high efficiency boilers nowadays have the intelligence on board to send a remote signal, like a 4 to 20 milliamp or a 0 to 10. And then the key is to have the pump that's sitting there have that onboard intelligence to receive that external signal. So it doesn't necessarily maybe have the drive, the information's coming from the plant, the firing device, but it has the intelligence to receive an external signal and respond its speed according to the power input. And so they'll fall in line. I mean, there's a little bit of magic going on behind the scenes, but it is a way of doing that. Absolutely. So anyways, all we're just referring to or showing here is you plug in to this variable frequency drive, this control, whether it's a full blown with remote sensors, if it's an onboard, and it's just looking at pressure differential, motor torque consumption, torque of the motor, or even an outlet sensor on the pump. We want to have these system conditions. So fixed, constant, branch, head loss 24 feet in this example, and a variable of 56. Where's the 56 coming from? Like we just talked about. It's these two guys. It's your distribution, supply, and return. And that curve would move up. So I'm going to have that system curve start from 24 feet and develop that curve from that point to, all the way through, but obviously up to our design conditions of 1115 at 80 feet ahead. So what are some of the inputs? What's your design flow? What's your design head? Here's that minimum control head. So you're putting in, here's my total, but here's my variable, my 56, and here's my minimum control head. So that's information this type of drive wants to know. So it's always maintaining at least that minimum control head. It's not, so it's starting its curve not at 0, but it's accounting for that circuit's controlled pressure drop. And then there's another thing that might say, hey, the minimum allowable, how low can you let that pump? How low can that speed go? Is there some factors? Minimum recommended speed by the motor manufacturer, typically 20 to 30% of the RPM. So 1750 times, 20% of that. That might be a 30%. The manufacturers will say, hey, we really don't want that motor operating. There's a range that's certainly fine and get all the benefits and the energy savings, but don't go too low, chasing ultimate energy savings and then damaging the motor or shortening its life. There might be some speed requirements to provide minimum equipment for the flow to the chiller, boiler, or heat exchangers. Kind of to your point, can we play with it? Yes, but there might be some minimums that we don't want to go below. So there's information there. And then that they refer to as the critical circuit, or the guy that has the circuit that has the controlling pressure drop. In this case here, we establish it. Typically, what happened is if you took that 80 and times it by 30%, you do the math. It's about 24, 25 feet ahead, and so that became our control or our constant head loss, and then the variable would be about 70 to 75%. So here's our 24 foot. Maintain that. Create our control curve, or it's a system curve, but it's really a control curve because it's accounting for that minimum 24 feet. So now what it's saying here is, hey, valves are closing, I'm backing up on my curve, and now I'm pumping maybe 820. I get all the way down to maybe in this case here 510, half of that 1115, or give or take. And what is it doing to the efficiency of that pump as far as the selection? It's still staying at a pretty high range of efficiency. So the speed reduction is occurring, the turn down. I'm still maintaining that minimum control head of that 24 feet for that branch. And so that drive is just constantly doing that. You're selecting at the beginning, the contractor or the controls guys that are setting up the operation, they're inputting this information that we're going to provide to them, and then kind of get out of the way. Just let it do its thing throughout the course of that heating or cooling season. And you might get into multiple pumps where, one's a 100% standby. That's obviously a pretty standard design, because I can't not have performance. So I got to have 100%. I maybe do some rotation. There might be some logic on board that says, hey, every X number of hours, I'm rotating and stuff like that. I have a failure. I sense that failure through some type of current sensing, pressure difference, something that feeds back and says, hey, bring on 2. Something occurred with 1, create an error message. Maybe it gets into the building management system. But that's pretty standard stuff to see. When you guys get into that commercial space, they're going to want 100% standby. What they're talking here is, it's kind of crazy, but if you set the control head from the mechanical room, so it's a pressure differential just leaving that mechanical room across not all these individual circuits, but just supply return, all of a sudden that constant head loss is a pretty high factor. You're kind of losing some of that benefit of what we were doing back here with only 30% and a 70% variable. Now they're saying I might have a 90% constant and only a 10% variable. And the system pressure drop was 72 feet ahead at that point. So you can see how it really impacts. You don't have much to play with, So it's a I don't want to say it's a technique. It's a control strategy. It's missing a lot of benefits, using that mechanical room head loss versus getting out remotely into the other buildings or remotely out into the terminal unit. But as it's seeing its reduction, it will reduce to a certain point, but it can only go so far. So that turn down is that range in here, because it's being told, hey, my control head minimum is 72 feet. Because I didn't get out into the system. I'm just looking at supply leaving the plant and return coming back. It's a pretty limited application. So what is the control area? Multiple sensors. How many sensors do you need? What's the area? So you've got a lot of stuff going on here. We've got the production, boiler, chiller. We've got our distribution. Again, these could be different parts of a building. These could be different buildings. I might have a minimum bypass flow just to satisfy the pump. He might have that minimum, and so as I start to get close to that minimum, I'm going to open up this to, I don't need it out here, but I have it back here to satisfy the motor manufacturer's minimums. A control area represents, the flow head operating point possibilities. So you've got that, like we said, that static or that control head, and then you have the variable. And that's going to change based on flow. One of the things I'll talk about is to get into this branch to riser pressure drop ratio and how it impacts the control area. So what they're talking about here is this: branch to riser pressure drop ratio and the control area size. So I have an A to B and I have a C to D. And then I also have a branch, and that's what they'd refer to as the branch. So what's that pressure drop there relative to this pressure drop and this pressure drop? and they're going to divide it. What's that ratio? And if it's really low or it's really high, it's going to impact the control curve of the area what I have to play with. The higher the ratio, the smaller the control area. The control area. Again, feedback. You know, I might do parallel pumping, and it might be 100% standby. So I'm just going to have this controller that's going to operate. I got some remote feedback. Could be 4 to 20, could be 0 to 10, whatever the case may be. But feeding back to the controller that then in turn brings on pump 1 or pump 2, whatever the case may be. So, you know, what type of feedback sensors? How many sensors do you need? Where do you locate them? These are all different. You know, we're not going to solve all of that tonight, but these are the factors that you want to be aware of when you're getting into designing or selecting variable speed applications. So, and then what they'll talk about is just some quick, you know, kind of standards, what type of feedback, maybe where you locate them. Common feedback sensor pressure, change in pressure at a single point. That might just be like a booster, a potable water booster. You know, as you got a discharge, you want to maintain X, 80 pounds, 60 pounds, whatever that number is. And as the load's changing, instead of just keeping that booster pump at a constant speed, I can provide variable speed of the booster. So if there's a lot of load going on, the pressure's dropping, I'm ramping that booster package up. And as the load's reducing, I can ramp that booster pump down. Differential pressure, change in pressure points between 2 points. That's going to be what we just talked about, heating and cooling. That's going to be our chilled water and our heating plant. If temperature, maybe it's just a change in temperature, could be batch. I mean, these are just some different examples of, this is the world you guys are going to live in, I think, for the most part. HVAC, heating and cooling, and then perhaps some pressure booster packages with potable water. I don't know if you want to speak to that at all, Will, but I think these are these two guys are going to be the most popular of the everyday versus, you know, you're getting into manufacturing. Differential temperature, that could be another feedback for whether it be solar or water heating. I guess you could get into the air or water side of HVAC coils. A flow meter, which is just going to measure flow rate, that would feed back for process. Where do you locate them? A differential pressure feedback, the mechanical room, 2/3 of the way out, somewhere, you know, as far out as you can, relatively speaking. The most remote hydraulic head loss circuit pump, you know, that will serve as that critical circuit. So, you know, these are just different factors that come into when you're actually applying and installing or designing, you know, that VFD and how do you want it to do what it's going to do. These are just getting into different examples where you have that, you know, here's your design condition on design day, 1,000 at 120. Here's that differential sensor, DP sensor, maintaining that 24 foot that we talked about. And as you're getting into pot loads, all of a sudden the flow rate's cut in half, perhaps. And so the pressure drop, obviously, excuse me, is changing to 120 down to 30, because that's that squared relationship, cutting the flow in half. But I'm still maintaining that 24 foot across that control circuit or that control head. You know, how does that come into play? That gets into that control area, or what are my options? So again, talking about where do you locate? You know, do you get as far out into the system, that critical or that branch or that circuit that has that, you know, greatest head loss, that constant head loss, and then the distribution becomes the variable head loss. And then I guess it gets into, you know, what's the percentage? Is the variable only 50 versus 70 and the constant is 30? As you get into, for whatever reason, where that constant is playing a much higher factor, it's going to impact how far we can ramp down. We're going to be limited in that range, limited more than if we were running it at that 70% variable. And then if you get into some mechanical part, perhaps really limited, that's kind of what we talked about, where you're just measuring right in the mechanical space itself and you're not taking into account what's going on out here. you have a very limited variable range because the variable head loss is so limited to just this range here. So, there's just a little bit of, some thought process as to how we want to apply what we want to do out in that system. Sensor locations, all terminal units loads change at the same ratio. Head loss of supply return mains is less than the highest pressure drop of that highest branch circuit head loss. All branches have a similar head loss, no more than 25%. If one branch does have a greater than 25, that's where that sensor placement might be recommended to maintain that minimum head loss. So again, there's more and more feedback. Ideally, that's your critical. That's that one that's maybe causing the highest or has the highest pressure drop for whatever reason. That's what was going to become our constant head loss, and we're going to vary the 70% on our distribution supply. It'll be coming up on ECM. Yeah. How it establishes that. Yeah, correct. So this is just also going through something, what's taking place as system conditions change and how it's backing up on its curve, or the load changes. The point of it all is ASHRAE is really, pretty descriptive, if you will, or saying, hey, this is to apply or to provide to your client energy savings. These are some of our standards that we abide by or want the industry to abide by. And it's almost any hydronic system we talked about earlier. It's like 2 or 3 horsepower and above they're gonna want to see some type of speed control, some type of drive. There's an option out there, or there's a thought process, a strategy where if you're getting into DDC systems and you might take the feedback of valve positioning to influence VFD drive. I don't know how much we play in that space. It's typically what we're going to get involved with is going to be more some type of pressure differential and DP, differential pressure sensors, either in the mechanical room, halfway out, ideally all the way out. But another strategy out there is to use that DDC and start looking at the valve positioning as a means of feedback to increase or decrease speed of that distribution, that secondary pump. So let me jump into our next subject, if you will, which is called the ECM pumping. So let me just close this down real quick. I'm going to stop here for a second. I just want to let's see here. I'm going to close that guy down. That.
So George just sounds like he covered quite a bit there. This class, at least all the topics we have in here, I mean, you could turn into its own series. So if any of this stuff you want to go a little bit deeper into, or something that maybe would be more of a complete discussion over, we can do that. So if anyone shoots either one of us an email, we can run through those. But we'll send out all these slides, and so I'd like to do that this week so that you guys could go through and say, okay, this slide I'd like to know more about, or
before we get
maybe
back
a lunch and learn on this topic.
Right.
So
yep, absolutely. Is that popped up on your screen? Okay, we're good to go. We said we typically don't sit here and talk about our product versus their product versus XYZ product. This would be just a quick example, but again, it's more about the application. This is our version of that technology, that ECM, electronically commutated magnetic motor. And this technology's been around for quite a while in Europe, and it's been here in the United States for a period of time. And it's becoming a pretty standard way of controlling or providing a circulator that or a pump that can do a bunch of different or has the ability to operate in a bunch of different modes by having on board some intelligence, printed circuit board. It's got some software. And so all of a sudden, it has the ability, by just configuring it, setting it up in the field, I can take this one pump and maybe apply it to 4 or 5 different modes, depending upon the application. And it's coming, as it's just trying to emphasize here, as far as voltage, single phase and 3-phase. So just real quickly, what's different about the pumps? There's magnets, electronically commutated magnetic motor. There's a magnet that's on the shaft or surrounds the shaft of the pump, of the motor. And that's different. And so the magnet on the rotor, eliminates the input power to magnetize. The stator coils generate a rotating field, and the magnet just reacts to this change. So opposites attract, if you will. We'll give you a quick example of that. But the magnets on the rotor react with this magnetic field, and it causes rotation, spinning, RPMs. The motor itself is microprocessor controlled. There's software, there's some brain power right on board the pump coming out of the box. We're not adding an external drive. It's there, it's on board. And basically, and this is the part about the commutated, but power is pulsed on and off electronically to create the magnetic field in the stator. The process is referred to as commutation, but it's a very simple, but kind of a picture speaks 1,000 words. The green, color green, represents the North Pole, and the red is the South Pole. So this is the magnet that's on the rotor that's rotating. And what's on the end of that rotor but an impeller sitting inside that volute that's moving GPM and overcoming pressure differential. And so power is pulsed on and off electronically to create the magnetic field. And as this is pulsed, the magnet reacts. So the faster it's pulsed, the faster this thing spins, this rotor spins, which means maybe increasing the flow rate, overcoming some pressure differential. And then conversely, if system conditions change such that maybe I don't need all of that flow, then it will start to change the pulsing of that electronic or that magnetic field. And all of a sudden the speed starts to slow down. And in doing that slowing down, it's changing its flow rate, but it's also changing its energy consumption. Just like we just kind of hopped on those bigger commercials with the external VFD drive, same concept, it's just doing it on board internally with some software and a printed circuit board. Yes, yeah, 3 horse and under, 3 horsepower. Correct. And I don't know if it's physical limitations. I don't know if it's economics. Bigger. It's all about speed control, to your point. Right. Correct. Just kind of, and again, these are kind of universal icons, if you will, but they're just talking about the different operational modes that are on board, built in on the software of the pumps. So they'll have what they refer to as a constant pressure, or another option is proportional pressure, and constant curve, or sometimes it might be referred to as constant speed. And we'll go into some of the examples and where they kind of fit in our world in the heating and cooling industry. And it's happening on an everyday basis. Within these modes, they actually offer this additional energy savings feature where you have some night setback capabilities, whether it's chosen or selected out in the field. That's kind of an individual preference, but they do have that as an additional feature. And so kind of jumping, I guess, into the first, proportional pressure. And typically what they're trying to say is the pump pressure is continually adjusting itself based on flow demand. So you have this design set of conditions. I've got, an apartment building with 48 units. There's a certain BTU load. I've established a flow rate. And then I have these 48 apartments, and say one of the guys with the greatest pressure drop or the furthest out has a certain pressure drop of, pick a number, 10 feet, 6 feet, 8, whatever that number is. And so in theory and design conditions, when everybody's calling, I've got a certain flow rate overcoming this pressure drop. And then as the thermostats within those apartments or the valves start to close because of space temperature, instead of trying to still provide that same capacity, it's going to say, hey, there's a load reduction. I can incorporate a speed change because I don't want to develop that additional pressure. If I stayed on my curve, as I start to reduce the flow, I start to back up on the curve, I would develop higher pressure differential. So I sense that, and I'll start to back down that speed to fall more in line with what the system conditions are at that given point. We'll talk about it. The point of it all is that is typically where you have a distribution pump or a single pump. You might have a parallel in terms of backup, but a pump that's feeding a bunch of terminal units that have their own individual control. So those valves are opening and closing, modulating or on off. And so as those system conditions change, this pump will automatically respond to those system condition changes. And in doing so, change its speed, ideally lowering it, ideally consuming less energy. That's the feature. Proportional pressure. Absolutely. Yep. And so these are just a couple of different, very, very basic stuff, but a lot of it came initially when it came over as far as the hydronic side is Europe is all ECM motors. It's all proportional pressure. Residentially speaking, there's only one pump. They don't zone with pumps. It's not uncommon here in the United States where if I have 3 or 4 zones in a home, I might have 3 or 4 pumps. Each one's kind of dedicated to that zone, just the way we do it. Over there, they were maybe a little more energy aware or trying to reduce energy consumption. And their thought was one pump, 3 or 4 or 5, whatever that case may be. In this case, it might be panel radius that might have some type of non-electric valve that kind of floats opening and close based on conditions in that particular room that panel's located. But it's changing pressure conditions. And so the pump senses that on board and it's going to change its speed. So that's what drove it. That comes over here. We have systems that do incorporate non-electric, but we also have systems that incorporate a lot of some type of electric, perhaps open close, or it could be modulating, but most of the time it's going to be an open close valve. But at the end of the day, those system condition pressure changes occur, the pump reacts accordingly with that proportional pressure. I don't know if you guys have ever even heard of or come across a thermostatic or a non-electric valve. That's what they look like. Just a quick picture. But it's self-contained. They're all over Europe. And in certain cases, college dormitories, sometimes apartment buildings, you might find them, in those applications as well. It's a kind of an inexpensive, no wires. It's its own little boss right at its location. It's got an actuator here that's sensing airflow, and based on a dial setting that whatever that mixture is, copper, beeswax, some type of element that responds, expands, contracts based on changes in temperature, will open and close and move that port a little bit open or closed. So that's just what a non-electric valve is. And what this is trying to show here, and what Will was mentioning a little bit earlier, is like, how does that proportional pressure curve work, or what takes place here? And so it's a very simple, simplified example, but what they're trying to show here is, in this case here, it's a very simple, I've got all 4 zones and they're all running. And I just happen to call it curve 3 is the right set of conditions for all 4 zones to operate. So this is my flow. This is my desired head. This is my curve right here. Yep, jump in. design head meaning this, right? So in this case here, maybe if I didn't have these dials, commercially speaking, I'd be picking 10 feet ahead, or 15 feet ahead, or 22 feet ahead, whatever that design that you've calculated, someone's calculated, saying, hey, I need this flow at this head. That's what we would dial in. This is just, again, simplified. It came from our residential pumps that, same concept, they just put in these dials for the contractors.
And so commercially, just what you would see is, you see how we have the diagonal, let's say 3 to 5, or curve 3 goes from like 10 to 5. Commercially, it's about, you have your H1, and that would be the star is, and then take half of that head pressure, go to the y-axis and draw a diagonal, and it somewhat aligns with that, but that's what you're going to be thinking of commercially as George goes through this.
Right. Did you get
Yeah,
that? H1 and H2? And that's all about the proportional pressure. Is whatever your design head is, and you say, hey, pump, I want you to be in proportional pressure, I'm going to take that H1 and divide it by 2. And that's going to become my that's my H2. So when it has that kind of like, I don't know if you want to call it a bump or whatever, but each one of these curves, on the right-hand side of that curve right there, just for example, real quickly, 4, anything to the right, that pump's running at full RPMs, full speed. And then anytime it operates to the left of that hump, still speed control, but now it's less, it's reducing its speed. And that's the energy savings. And so they'll establish, hey, and it's kind of it's a industry standard, if you will, 10 feet ahead divided by 2 is 5 feet ahead. So my proportional curve is going to be maximum conditions at 10 down to give or take right around 5 feet ahead. If I get 25 feet, it's around 12.5 feet. So as you look at that curve, to the right of it, it's full speed RPMs. To the left of that bump or that hump, it's speed control, and you're reducing, which is where all the savings comes in, which is why the utilities are all interested in all of these technologies that introduce speed control, which means kW reduction, potentially. So all they're saying here is, as you go through and say, hey, zone 1 closed, or whatever the case may be, one of them closed and I got 3 open. Well, instead of an old pump, a traditional, no speed control, no smarts, he would just back up on that one curve because that's all he would have. So he'd just back up and develop all this excess energy and continue to consume the same wattage. But because he said, hey, I'm mapped, I've got this onboard printed circuit board that says, hey, you in this case selected 25 feet ahead, or in this example, you selected curve 3. I know where you're supposed to be based on wattage and speed, RPMs, speed consumption, speed control based on wattage and RPMs and wattage consumption. And as it starts to change, it says, hey, and it's in a split second. It's not like, hey, I'll go back. No, it happens right away. So it will follow that curve. And then additional zones close. It's sensing that, and it's slowing itself even further. And again, it's a very simple little, but that's a kind of a quick example of how proportional pressure, whether it's this little silly diagram, or if it's a good size, light commercial building out, out somewhere in downtown Boston or wherever, you introduce this type of pump or this type of operation, that's what's happening. And it's happening constantly. As valves are opening and closing throughout the heating season, for example, it's constantly riding back and forth on that curve to satisfy whatever the system conditions are. So this is just a behind the scenes, but it's all it's showing is it turns on, it's got a reference point, and there's an error that's existing. Or is there an error that's existing? And if it is, it recalculates and it adjusts that speed accordingly to stay on, in this case here, stay on a given curve or a given set of conditions that you told it, because it's all based on the design. So your design is 100 GPM and 25 feet ahead. Okay, I'm going to operate. Design conditions, I'm giving you this. Less than design, I'm backing it down. And it's based on that 25 feet, cutting it in half, following that proportional pressure curve. Here's just a quick snapshot. I'll say a more commercial, so a 65, 130, they refer to it as that 130 is talking about maximum flow rate. So in this case here, if you look at the pump curve, GPM 125, right about 130, the 65 represents basically maximum pressure differential in feet of head at shutoff, so no flow. So actually the model numbers kind of reflect a little bit what the pump's capable of, which is kind of a first for B&G. They'd actually look at a model number and say, oh, okay, I can visualize that curve a little bit in my head. But the point of it here is I'm doing proportional pressure. I have this set of design conditions and it's 75 at, pick a number, 30 feet ahead or whatever the case may be, or 28 or whatever. And I'm doing proportional pressure. I'm going to take that H, I'm going to divide it by 2, and that becomes my H2. When you look at it, you're like, doesn't look too impressive. Like, what's going on here? That's my speed control from maximum RPMs down to this. But when you look at the next curve, which is your wattage consumption on these RPMs, you're going from 700, 750 watts to potentially down to 400, 350 through 270. That's the savings. So that wattage curve is a little more reflective of what's taking place, even though it's the exact same curve as this. This is just showing the speed. This is showing the power consumption as you change that speed. And that's, so anyways, that's proportional pressure. Any kind of multi-zone, whatever the application, condos, apartment buildings, office buildings, school, dormitory, whatever. Another mode that exists is constant speed. And you say, well, what's the benefit if you're really not changing the speed? And I guess the only way we kind of look at it and say, hey, it can make some sense is you've got this pump that has this maximum curve. And all of a sudden you can dial in and say, you know what? I don't want you to run out here. So anytime you call, what they're trying to show with this drawing is when that pump comes on, there are no bunch of different little zones, terminal units with their own valves. It's just on. It's got a fixed load, a fixed flow. But I can at least dial that pump to what that flow is, what its need is. So I don't have to run it at full speed all the time. And I don't have to go through the expense of some external drive, perhaps. I have it on board. I can select constant speed and say, hey, I only need you to do X. These are my set of conditions. Pick the RPMs. So again, from consumption, I turn on, I'm consuming, but I'm not consuming as much as maybe if I just let it run wild and go to full capacity. I can dial in the pump to meet a specific application or set of conditions. It's a little bit of a drawing in a housing authority. These two guys are your distribution pumps that are going out to X number of 20, 30, 40, 50 zone valves. These two guys sitting right beside it are they're perhaps domestic hot water for that apartment complex. And you've got some coils sitting inside here. They're called indirect water heaters. Back in the corner here on the other side of the room is a cutaway of an indirect tank that's got a stainless steel coil inside there. But that's how they produce their hot water. The benefit that what I'm trying to show here is proportional pressure, constant speed, constant curve. So I can dial in that pump to say, hey, what does that indirect domestic hot water manufacturer say? I need this flow rate from your boiler plant through my coil to give you this capacity. What do you need? How many gallons of hot water do you need to satisfy your? I can actually dial it right in. And then I can have a standby. So I can have some backup. I can have some, so there's some features that are built in for that same pump. Just change its mode. I'm going up to the building proportional. I'm doing something more constant speed, dial it in. So it's got some flexibility. Correct. Right. It'd be something that's that communicating wire that Will was just describing that would go. So there's three specific terminals. And when they power up, you know, there's a little bit of setup time where you want to say, hey, you're going to be the lead guy and you're the follower. And then I think it's built in 24 hours of rotation of operation. It'll switch back and forth. But if there's some failure and all, so there's parallel operating modes. Again, same pump. You just selected it for this application. You can do parallel with, you know, speed control, proportional pressure going up to the apartment building, you know, and you get a backup. So of the 4 modes, there are 2 that make sense and the 2 that they just put in there because it's software, so you can put it in there. Backup operation, hardly ever selected. It says, hey, only lead pump runs and the second pump starts if there's a failure. Alternate operation says only 1 pump runs, but it switches every 24. So there's, you know, equal runtime, if you will, on both circulators, both pumps. And the second pump will start immediately upon failure of the lead. So to me, that's a very common, almost all the time. You put 2 pumps in, you get a client that says, I can't operate with a pump down. I need to have that backup. Here's a quick solution. The other thing is a little bit of engineering involved, but you can get into parallel operation where you say you have 2 pumps in parallel. And if the conditions are such that I can run both pumps simultaneously and I'm doubling my flow rate. So I have 2 300-gallon a minute pumps. I get 600 gallons a minute. I get 6 million BTUs with 2 smaller off-the-shelf pumps, maybe. And then it has some intelligence that says, hey, the conditions on the system are such that I don't even need the backup pump or that parallel pump to run with me. I can handle the load myself. And then as the load changes, I'll bring them back on. So there's some intelligence on board for this automatic parallel. And again, that 4th operation, they refer to it as, I apologize for that, fitting that symbol, but it's forced. So now it's just automatically on, no intelligence, just both pumps running all the time in parallel. But these 2 guys, and of these 2, that is by far the most popular. It's a convenience. You don't need that third-party rotation and all that. Actually flow, right? It's a nice solution. This is just a quick picture. A guy had taken it from the field and sent it to us. But the thing about it, you know, and again, with some intelligence on board, now I can see some operation. I can see exactly what's going on. So in this case here, I can see wattage. GPM is what that says. So I'm just talking about flow rate. What's this pump doing right now in this particular set of conditions? If I was hit that button, I could see what's the feet of head it's developing. And then the last one would be RPMs. So power consumption, flow rate, feet ahead, RPMs. The standby, or the guy that's my follower or my member, he's in standby mode. So it's telling me. And then what would happen is you came by, say 24 hours later, this guy would be displaying standby and he'd be running and whatever the set of conditions are when he took the picture of the flow rate and all of that. So that happens kind of automatic. It's a nice little feature. It's on board all of these. And to Will's point, all of the manufacturers, pump manufacturers, are going to offer some version thereof because they're all intelligent pumps. Another capability is temperature, measuring temperature, and it can be just a outlet temperature with the onboard sensor that's built into the pump on the pump head. So call it where the pump's located, say the supply. Another option is you can add a second external sensor, temperature sensor, and do a delta T. Maybe that's an option. It's another capability, another mode that's available within all of these style pumps. So adjust the pump speed based on a fixed temperature, or a delta T, change the pump to maintain a differential. This last one I just want to talk about to make you aware, because this is the second. Will had mentioned that proportional pressure is by far the most popular application out in our industry. This might be coming close to the second most popular. And it has to do with where it can take an input, 0 to 10 or a 4 to 20 input from, in this case, we're going to jump into possibly say a boiler plant. So a boiler that has modulating firing rates, and it needs a certain flow rate through the heat exchanger, but that flow rate can really change based on the firing rate of that boiler plant. So why have that full flow, tighten up my delta T? Let's keep that delta T fairly wide by slowing the flow rate relative to it. So this has onboard intelligence to receive that external. And then if you attach it to some boiler plants that have the ability to send that signal, that's a pretty good marriage. And again, that happens all the time. But this is just shown as a line, if you will, going from whatever that signal is. In this case, maybe 0 to 10, and then it kind of explains how the pump responds to the input on, off. It's speed control. When it sees that external signal that comes in, it immediately kind of loses its brain, and it just responds to the power input, and it ramps up, ramps down. And the feedback that's saying, hey, I need more or less, is not coming from the pump. It's coming from the boiler plant, in this case, something external. So just real quickly, if you went through a quick example where you had a couple of boilers, in this case, maybe they're boilers, and you had a distribution pump, and you were sending out, heated water out to a building, or whatever the case may be, whatever that load is. And what they're trying to show here, it'll make a little more sense perhaps next week when we get into this whole concept of primary, secondary pumping and what that all means. But I have a production side with a flow rate of 150 gallons a minute to one boiler that's up and running. I have, maybe in this case here, my secondary pump is running and he's providing, it just happens to be the same flow rate at the desired outdoor, based on outdoor temperature, 140 degree water temperature going out to the plant. And as it does its thing and it experiences a load, it comes back, and it comes back at 100 degrees. So it's taking that 40 degree delta T. Maybe it's by design. And so I go out at 150 gallons a minute at 140, come back at 100. I got a boiler plant that's firing at 150, a flow rate pump that's flowing at 150 gallons a minute, entering at 100 and discharging at 140, matching the load. What's the BTUs of that boiler? If I got 150 gallons a minute on a 40 degree delta T. I mean, it's just, you could take it through 150 times what? Normally we'd say a 20 degree delta T would be 10,000. So a 40 degree would be 20,000. So it's a 3 million BTU boiler at 150 gallons a minute with a 40 degree delta T, say, just for argument's sake. This is the ideal set of conditions that almost never exist, where this firing and flow rate at the production exactly matches what the building needs. It's utopia. It's great. It just very rarely happens. So then you could say, okay, something changed and the load out here changed. There's more zones calling or whatever. And the flow rate increases, so that 150 goes to 200. So if I'm pumping 200 gallons a minute in the building, but I still only have the one boiler firing at a flow rate of 150, I've got two different pumps. I got two different flow rates going on. What's going to happen is, as that 200 comes back, 50 is going to move up what they call the common pipe or the decoupler. And it's going to move up with a 50 gallons a minute at a temperature of 100 degrees, because that's what's coming back. The remaining 150 at 100 goes to my boiler plant. Does what it was just doing before in the previous slide. Provides that 3 million BTUs, 140 degrees. Oops. Now I have 50 of 100 mixing with 150 of 140, and all of a sudden I have a reduced temperature of 130. The reset control that's controlling all this plant say, hey, the set of conditions, I wanted you at 140. You're only giving me 130. So what does he do? Boiler 2 comes on. Now boiler 2 fires. I've got my 140 back to satisfying the building load. But with these two boilers running at full flow on the pumps, I've got now 300 gallons a minute in this loop. I've got my 200, which is fine, satisfying my clients out here. But now with that 300, 100 gallons a minute of heated boiler water moves backwards in that common pipe now. And now what am I doing to my return temperature? I'm heating it. I'm elevating my return temperature that's going back to maybe my condensing boilers that want to see cold temperature to really condense, to really achieve the efficiency that your client, asked you to specify and install in my boiler plant. So again, a set of conditions that we're trying to avoid is I don't want to take hot boiler water and elevate my return temperature. I don't want to do that, but I have to in this case because I'm responding to building needs. So I can start to impact as you start to change the return water temperature, you start to lower the efficiency. Now, it's in this case, some people argue, say, well, it's only so many points. Yeah, it's true, potentially, but over time, overheating seasons, you don't want to design a system that's continually degrading your efficiency just because you're over pumping, because you're responding to some system conditions. If you apply some intelligence, and that's what we're kind of leading up to. This is just kind of a snapshot. It's a very primitive, simple 500,000 BTU boiler, and it has a fixed flow pump that we just described with those 3 million BTU boilers with 150. And what's going to happen is the firing rate could modulate down. So I guess before we go any further, why does the firing rate reduce? I mean, it has the technology to do it, but why would it? What system conditions would say, hey, do this? The load's reduced. When you size that boiler plant, what are you sizing for? The warmest day of the year? No, right? Design conditions. And then maybe a little CYA just to cover your tail because, you don't trust anybody. But the design conditions are for what? 3%, 2%, 5% of the heating season? So most of the year it's less than. So if I have modulating capabilities, it's going to take advantage of that. It's going to say, hey, the system conditions are X. It's only 42 degrees out. There's a heat load. It's just not designed. Change the firing rate, saving consumption of fuel. But if you do it at a fixed flow on the boiler pump and you're reducing the output, as you reduce the BTUs, think about that scale 1 on that system sizer. If you've got a fixed flow rate and you have these different BTUs, look at what happens to your delta T. It goes in the opposite direction. It gets tighter. So all of a sudden the reduced output at the fixed flow, I got a 4-degree delta T across that heat exchanger. I'll hit that limit. I'll shut that sucker off. That's the last thing you want to do with this high efficiency technology. You want to bring it on and simmer and just let it percolate and slowly bring it up, bring it down as system conditions say, hey, I need more or less. But when you're cycling these things on, they got pre-purge, post-purge, ignition, heat up, cool down. We don't want to do that. And if we can avoid it, let's do that. So the next step, if you will, in the progression is say, hey, why not provide a pump that can vary its speed based on the requirements of the request from that boiler plant? So now we say, hey, I've got some smarts that can send a signal to my smart pump that can receive that signal and respond accordingly, change its speed, which means its GPM. So in this case, very simple, as it reduces its firing rate, let's reduce the signal, which reduces the speed, which reduces the GPM to try to maintain. So maybe the logic will be on this heat exchanger that sits inside this box that we can't see, there might be 2 sensors, an inlet and an outlet. And you were told, hey, when I configure this intelligent brain, let's maintain 20 degrees or 25 or 30, pick a number, but 20 degrees. So he's looking at this and this, he's changing his firing rate, and he's seeing that the delta T maybe starts to get a little too tight. Hey, slow down the power to the pump, which is going to slow down the RPMs, which is going to slow down the GPMs. So now I'm maintaining at 20. I have a much better chance of keeping that boiler on at that lower firing rate. So I'm not seeing that really tight delta T across the heat exchangers. So there's a lot of operational benefits of varying that speed with this fairly expensive investment, for lifetime, long time operating life cycle. So that's becoming a very common, behind the proportional pressure distribution out to your building, this is becoming a very common, and because those pumps, all of these ECM, these light commercials have this capability on board. You're not adding this third party thing. It's there. You just select it. So you can have your distribution, same pump, using it as speed control to control the flow rate across a condensing modulating boiler plant. It's pretty good, and it's become very common. On the resident, yeah. Right. For that exact purpose. Conditions on a building or conditions on a residential home. They all subject to the same laws of Mother Nature. As things are changing, the load changes. And again, it's just chasing after efficiency. So that's a pretty good, just one quick thing, and to try to tie it in, because we're going to get out of here at the end of the day. This was just a screenshot of a boiler plant. And the point of it all is boilers, these high efficiency boilers, we don't want to cycle them on and off, or we want to try to avoid that. And on an application that took place somewhere in the Metro Boston area, they were looking at these screenshots, and they were doing this. They were doing proportional pressure out to the units, and then speed control on the boiler pumps to the boiler plant. So they had some run times, boiler run times of 1,550 hours, and they had cycles of 131. So when you do the math, the boiler cycles are almost 12 hours a cycle, as opposed to 10 minutes out of an hour. When you have hundreds or dozens or, tens of cycles per day, because as you start to cut up the boiler plant relative to the overall load, modulate it, and then control the speed, the GPM through the heat exchangers to keep that kind of wider delta T, you get these boilers to sit on for a long time, which is beautiful, very efficient, both on the fuel consumption side and the electrical consumption side. So it's kind of a nice you put a little bit of thought into that design, take advantage of some of the technology that exists out there. You can make a nice, efficient plant, We don't have to get into that right now, I don't think. You guys, if you could see what I'm looking at, you're done. You're ready. To Will's point, we're going to get week 1 and week 2 PowerPoints and PDF out to all of your emails, both virtual online, as well as everyone sitting here this evening. Want to say thank you very, very much for coming for the second week. Full attendance. That's pretty impressive. And I guess we'll see you next week. So thank you very much, everybody. Appreciate it.